Uh, Today we have the next part of the topic. It's on active power frequency control. Third part, where there will be discussion on supplementary control we apply in an interconnected system. What we discussed yesterday, it was about the supplementary control in an isolated system. And if you refer to the slide that we discussed yesterday, so we have this supplementary control, this loop included as a extension of the primary control loop. So it is this one with the loop defined on the governor. And then we extended dial omega with the integral controller. And then this output of the integral controller will schedule the amount of power change on the turbine. Now, this for the case of isolated system supplementary control, we apply on selected units here. And it will be based on which generation, what that means, which generator or this power plant in a given area is more economical in terms of power generation. So the supplementary control is normally on economical power generator, basically. And it is through the integral controller. And here we had it for isolated system. So it means you may have several generators in the power plant, or maybe one or two power plants in a given area, but it is a isolated operation. So you don't have that area being interconnected to another area through the tie line. So it is an isolated operation where you have the supplementary control being achieved through integral control design here. The next part that we have, we start from here. This is about the load frequency control, or AGC, automatic generation control. We refer it for interconnected system. So, and this is the third part for the LFC problem. So, in respect to the active power control or the frequency control that we apply in the interconnected system. So, in the interconnected system, you may have, let's say, several power plants. It could be in one area, and then again, several power plants in the another area, and then these two areas, they may have their own load as well, individual load, local load, or they may also feed power to a common load center. So you have one area with several power plants, another area with several power plants, it can be, and then again, they are feeding power to a common load area. So as such, you may have two, or in fact, more than two number of control areas. So as shown over here, there are only two areas, but we can have one more sets of the power plants in another area, and then they may be interconnected here. So you have in the interconnected system as such two or more independent control areas. And the generation within each area, they have to be controlled. So that means you schedule the output power from the generators in the each of these areas here. So thus the generation within each area, they have to be controlled. And that means you regulate the output power from the generators in the individual areas here. And since the system is interconnected, what you find it here, and as such, uh, we will have to maintain a scheduled amount of power flow through these lines, through these tie lines here, what you have. And thus, this principle, the control of generation or the frequency, what we call it as load frequency control or automatic generation control. This applies when you schedule the output power from the generator based on the load demand change. So what you find it here in this example, you have several power plants in the areas, they are interconnected. Now in this area, you don't have any load connected here as such, but in this area, you also have a local load. Uh, the schedule power flow, schedule output power in this area, it is something 1000. In the area 2, it is again as 1000. And here you have the load demand of 500. Now what you find it here that you also have power flow from this bus 1 to the load bus here, which is something 666 megawatt. And again, from this bus 2 to the load bus, again, this much power flow takes place. And again, between the two areas also, you have this much power flow. So here you have some exchange of power flow between the tie lines that is interconnected here. Right. So this is just an example. And if in case, let's say you have some load change here, or you have load change over here, then uh, what should be the change in the schedule power in this side, and then again on this side? So that we have to decide actually, so that we are
I have a
able.
question.
Yeah.
How do you determine the optimal power flow between the generators and the loads? Like, for example, you have a line here and two lines here, right?
Mm.
And each line has its own capacity, let's say. So each line can carry a maximum power of this much.
Mm.
And also the losses on each line are dependent on the length of the line and also the rating of the line. So is there like an algorithm that calculates what's the optimal power flow to reduce the loss and also
Yeah. Yes. Yes. Yes.
something like that?
Yes. Yes.
Okay. What's
Yes.
the
Uh,
which part of the system is this?
Normally, yeah, we once, let's say this is your interconnected system, and you have some load changes here. Then we decide what should be the change in the output power from the generators here, right? As a offline, if I have to say, we have the model developed for the system, and then for different contingency level, so you apply some load change here, you apply some load change here, and then for every contingency level, we regulate what should be the change in the power from this sets of the generator and what should be the change in the power from this sets of the generator. Then uh, in fact we develop a power flow equations, and then we have different algorithms. You can say the Gauss-Seidel method, or then another one is the Newton-Raphson methods. So we have these algorithms solved, that we call it as powerful algorithms, solved in such a way that the voltage, because these are the generator buses here, and these are the load buses here. So when we do the load flow analysis, we can consider one of the bus as a slack bus, and then with respect to the slack bus, that means the reference bus, we will consider the calculation, that is the estimation of the bus voltages here. It could be the bus voltage here or over here. Then again, what is the rotor angle? This could be the slack bus. So what could be the rotor angle here, or the bus angle here, or the bus angle over here? So we do the calculation or the estimation of all the parameters which are in fact related to the power flow in the system. We do that part.
I am familiar with both Newton-Raphson and Gauss-Seidel method. We studied that in undergraduate level.
Yeah, yeah.
But my question is, do they always give you a unique solution, or is there like, could they
Uh,
give you more than one solution and then you have to choose which one is best?
but again, we can because it could be a unique solution. In fact, otherwise, how can we say the optimal one? And but again, we we also apply because we have to schedule the generation change here. And when we have this schedule generation change, we try to have an optimal economic actually. So what will be the
Yeah, this is
minimum?
what I'm asking about. How
Yeah,
do you
yeah,
optimize the cost?
yeah. So we define an objective function. So let's say for the case of thermal power plants or steam power plants, so we define what should be the generation cost, right? Generation cost for each of the generators or the power plants in the system. And then we take into account what will be the power transmission loss in the network, and then the generation log cost and the power transmission loss. What will be the cost as a factor of power transmission loss? We take into account that part, and then we optimize it. So we formulate an objective function which will be as a function of generation cost and the cost of the power transmission loss that way. And we optimally obtain it. And then we try to minimize this cost, the overall cost. And then we say that, okay, it is this set of the generators, it should be that much change in the generation. And this should be the another set of the generator, we should have this much change in the generation output. That way we do it. We have the
Okay,
optimal generation scheduling.
that makes sense.
Yeah, we
But
do that.
do you know like which type of algorithm they use for optimizing this cost function, or what do you call it?
Uh, as such, in fact, we can have the because we have several optimization techniques basically, and it could be the heuristic techniques or meta heuristic techniques basically, or sometimes we also say the linear programming approach we apply that one, but more conventionally if it could be like genetic algorithm, PSO, swarm optimization techniques. So there are several of the optimization techniques which could be used for the optimal decision making in the generation scheduling part.
Okay, that's interesting. Yeah, I really want to read more about this. If you have a reference about these optimization techniques, it should be useful.
Mm-hmm.
If you give me maybe after the lecture,
Mm-hmm.
if that's okay.
Yeah, right. Yeah, you mean to say another lecture for the optimization part?
No, I'm
Uh,
saying if you have a reference that has these
okay.
techniques,
Okay.
I want to
I
read
will
about
find.
it.
Yeah. Okay.
Yeah,
Okay. Okay.
if
I
that's
will
okay.
find it.
Because you
Okay.
said there are many, and you mentioned the names I've never
Yeah.
heard of. So
Yeah. 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 No. No. We have several papers also, and then in fact there are some uh, system operators, the power plant operators. They use those techniques for optimal generation scheduling. So we have them that. We have them that. Okay.
okay.
Right. So this we have this generation control, but as I said, uh, the optimal power for solution which you talked about, this we do it um, in fact after the several time span. So it could be like say after a duration of several hours, or we do it uh, one at least for 24 hours and next for 24 hours, that way. But we don't do the optimal generation scheduling every 5 minutes or every hour. We don't do that actually, right? So but when you talk about the generation control, there the change in the schedule power flow, that is basically as you can say half an hour or every 15 minutes or even 1 hour we apply this, right? So that means what I mean to say, the time span for the operation of AGC, that is little bit shorter as comparable to the economic allocation for the scheduling of the power flow. That is little bit different way. But here we identified that, okay, it is this sets of the generator or the power plants which will be optimally in the generation and thus the cost, I mean. And thereby we can select that, okay, the it will be these sets of the generator which can have the automatic generation control applied. That way it can be, right? Okay, so we move next one. So then in fact, we have a hierarchy level of control function or the control action for AGC or LFC. And the one of, in the hierarchy is the centralized level. So the centralized level will regulate the amount of generation uh, for each area uh, to apply in the secondary control. So thus the centralized level control, their objective will be to schedule the amount of power exchange between the areas here. I mean between the control area, because each area they are defined as a control area here. So one objective will be to schedule the amount of the power flow through the line that connects the control areas. And also second objective is to maintain the frequency deviation uh, in the interconnected system to the set value. So that means whatever the correction which we have achieved after the primary control, further correction is applied and that will be through secondary control action basically. So this is just an example as shown here. So let's say you have an original situation. You have area control area A, B, and C, and the scheduled amount of power flow in the tie line that connects between A and B, and the direction of the power flow is this one between A and C, and then between B and C. But if there is some, let's say, uh, what is shown, this is actually out of an example I have shown, but I have not discussed what are the calculation part. But if there is a loss of 400 megawatt generation in the area B, in the control area B. So if here you have 400 megawatt outage of generation in the control area B. As a result, uh, the change in the schedule uh, for the area A and the area C, what you observe, the direction of the power flow. and then it is all towards the control area B here. So then again, that means in the interconnected system, whenever you have some contingency, here you have the loss of generation, but it could be also in change in the load, in the area B, area A, or area B or C. Right, it could be either increase in the load or decrease in the load. So whenever you have any contingency in each of these areas, there would be always a change in the scheduled amount of power flow in the tile line. And thus, being interconnected system, it is always possible to have a interchange of the power flow. Right. So because for the original situation, when you consider the power flow was from B to A, so it means that area B has surplus power generation available. Right. So, and that's why it was able to supply to area A and as well as area C. But in case of generator outage, uh, in area B, what you find, there is a deficit in the generation in the control area B, and thus the system being interconnected, you can have the power flow available from area A and C. And that means here you have increased the generation, that means area A and C, and thereby you are able to meet the demand what we have from area B, and this is possible only when you have the system interconnected. But when we have the system interconnected, it is require what should be the amount of power flow in the tile line. It should be as per the schedule value, and what should, because the system is interconnected, so it is also required to achieve minimum frequency deviation here. That is very important for us, right? Anything on this slide? Okay.
So in this case, the controller, can you go back to the slide?
Yeah.
In this case, the controller is determining this power flow from
Yes. Yes.
and the other contingency when you have a generation loss.
Yeah. Yes. Yes.
This is controlled by the secondary control.
It will be through secondary control. Yeah. How much should be the power? Because system is interconnected. So how much should be the change in the scheduled power flow from the generators in area A and C? That has to be determined, and it will be based on what is the dial F frequency deviation from the system. So according to that, you change the scheduled output from the generator, and thereby power flow through the line, because you have to change the turbine output power, right? So how much change in the turbine output power you should have, that is important, and that will based on what is the frequency deviation. And frequency deviation is again affected by what is the uh, contingency level, how much load has sent, or how much, as in this case, generation outage has changed here. So it will that, because any mismatch between the generation and demand will translate into frequency deviation. So thus the supplementary control will improve, or it will try to modify the change in the generation from the generators here, right? Okay.
Okay,
So
yeah, that
yeah.
makes sense.
So with this concept, then we move on to the how to model it actually, how to do the estimation, or like how to apply the supplementary control in the interconnected system here. So in this slide, what is shown, you have an area 1 and area 2, and the power flow is through a tie line, so it is a inductive line we have shown. And as it is indicated, it is power flow from 1 to 2. And the electrical circuit representation for the two areas can be something like this. So what you have it here, the excitation EMF of the AC source for the two ends, and then the corresponding bus angle or the rotor angle here. And then this could be the reactance of you can say the combined reactance of the generator and the transformer. And this is the bus here. So this is the bus for this AC source, and this is another bus for this AC source. And this is the representation of the line here, the inductive line here. So we have now, we can combine all the three reactants for the two sides and then again for the line itself. So this is the total reactance here, right? So from this,
What about the load? I don't see the load here in this figure.
okay, it is not shown, but we will come to later. We'll come to later, right?
Okay.
Yeah. We from the just I'm trying to discuss how we start with the uh, equivalent circuit representation for the interconnected system, and then what is the power flow equation. So we start from here.
Okay.
So then the amount of the power flow through the two areas, and that in fact from 1 to 2, we can write in the with this general relationship what we had that defined for the power flow through the tie line. So it is the product of the EMF at the two end and the total reactance of the system, and then the sign of angle difference at the two ends here. So I think thus we can draw along the y-axis what you have it here, the power flow, and along this axis it is the angle difference. And then here you have represented as a sinusoidal function here. So here it is at 90 degree, it corresponds to the maximum amount of power flow, maximum value. And thus we can linearize this equation, and let's say that delta 1, this is the initial state of rotor angle, initial operating point, I mean, and then we can write in this way. So with this change in the angle for the two ends, we write this way. And then here we have the T. This is basically the synchronizing power coefficient. We have linearized it by taking the partial differentiation of P here, right, with respect to the angle. And thus, this is the constant term what you get it, the synchronizing power coefficient as this one. Yeah. And then after substituting the initial operating point, so we have this one. So I hope you know how to linearize the equation.
Yeah, we studied this in advanced
Okay,
control.
yeah. So we do the partial differentiation of P with respect to the angle, because we here the P varies with the angle. So we do the partial differentiation with respect to the rotor angle here. And then now what you find it here, it is the same way, the representation for the system. What you have it here you can see the summation block. This one was the droop gain, you can say. You have the, oh, so sorry, this arrow direction should be this way, actually. It should be this way, not this one. So you have the governor, and then you have the turbine. This is the turbine output power. And then here you can see it is the inertia representation of the area 1. So this is the equivalent representation for the area 1. And here you get del omega. And when you integrate it, you get del delta here. So this is your rotor angle. And similarly, when you do it for area 2, summation, governor part, turbine, and then the inertia part, and the same way angle 2 here, rotor angle 2 for the area 2 here. And then you have this feedback through the droop, and the same way also you had it here, feedback, the area 2. And then here, what should be the power change you have? And you can see this is the turbine power. And then here you have the load disturbance here. So the error between the turbine power and the load disturbance will give you, in based on inertia, will give you del omega here. Now, the two areas, they are interconnected, and you can see the interconnection is based on these two parameters, the angle difference and the synchronizing torque or the power coefficient here. So this angle, these two angles and the T synchronizing power coefficient, that was not available when you had the isolated system, because in the isolated system you don't have any tie line, you don't have any power flow through the tie line, so system is isolated, so you don't have those variables. But for interconnected system, we have these two quantity, and then as well the synchronizing power coefficient, and thus they are here. So right, so this from the steady state frequency deviation, since the system is interconnected, so we write in this way. It should be the same for the two areas. And then if you have a load change, then what will be the deviation in the frequency? And then we can write in this way. So this equation, what we have written down, it is based on the previous formulation of the relationship that we had for isolated system. So this is you can see this is load change, and then your the equivalent, you can say the equivalent R here. And then what was the net or the total load damping factor for the two areas here, right? Is it okay, this part?
Yeah.
Okay. Andres?
Yeah.
Okay, then next we write down, so let's say consider that we have a steady state quantity. That means you have some perturbation, and after that there is no disturbance, so the system is at steady state. So that's for the two areas. We the change in the power. So what you have it for area 1 and 2, so turbine power, power flow, and the load power here. So here we have written it for del F times D1, and then for area 2 and this one. Now remember one thing, we have considered the power flow from if you have it this one, so we have considered the power flow from 1 to 2 here, right? And based on that, that's this del P12, what you have it, power flow is from 1 to 2, and that's why here you have the sign plus, and on this side it is the sign minus here, right? So that is important when you consider the interconnector system. What is the direction of the power flow? So it is the area 2 which receives power, and thus this is positive. And from the area 1, it flows out, and thus it is minus here. That point should be clear. Then for the load, you can say minus or plus is up to you here, right? And then accordingly, this for the area 1 and area 2, this quantity can be modified here. Now for the what we define the droop for the each of the control areas. So the change in the turbine power based on the droop in the area 1, and the change in the turbine power in area 2 based on the droop in the area 2 here. Then we substitute this, in fact, these equations, and then we obtained this form. So after manipulation,
I have a question.
yeah,
Here you put the load in area 1. Is that why it's in the equation on
this,
top?
yeah,
Does that mean the load is connected to area 1 or?
it is connected to area 1, yes.
Okay.
Okay, yeah.
Yeah,
But
that's fine.
yeah, fine. You're right, actually. So here we have considered area 1, but I have also shown area 2 also load, right? You can see,
Yeah. But
but
you did
here,
not consider
yeah,
it.
I have not considered, but you can always have it manipulated. That's what I refer
Okay.
to. That's what I
Makes
refer
sense.
to. Yeah. So because if for area 2, in that case, if you write minus, so it will be minus del P L2 here, right? It will be that way. So thus with the substitution of this, what you have it here for the two areas, the equation being written down in this way.
So just
And
as a reminder, this del PM1, what does it refer to?
which one?
Del PM1 and del PM2, these are the droop coefficient, or what's this? The droop?
No, R1 and R2, they are the droop, yeah.
Okay,
Right.
and the del
And del
PM.
P M1 and M2, they are the turbine output power.
Okay, the
Right.
turbine
So
output
yeah.
power.
So what we now see is you have interconnected system. Now let's say that you have some change in the load here, right? You have some load disturbance, either increase or decrease. In general, I'm discussing, right? Now, in that case, what should be the change in the turbine output power here? But since the system is interconnected, we should also consider what should be the change in the turbine power here as well. Am I right? It should not
Yeah,
be
and
just,
the change is
yeah,
found using the droop.
yeah. So it's not be
Okay.
just with that turbine power in area 1, but since the system is interconnected, we have to see what should be the change in the turbine power in area 2 as well, right? So it is that way. So we have this manipulation, and then solving that, we write now what is the frequency change here. So it is the same way what you had it for isolated system. So if you remember, we had this load frequency regulation factor. Yeah, that was the beta here, and it is this quantity, right? And then if you want to write the what is the change in the power flow through the tie line, it is this one. And then after, because it is my del P times beta 2, so we had this one, and finally we write it this way. So I think we have earlier referred what is the composite frequency response characteristic, because it takes into account the droop part and then again the load damping factor part here. So this is the
Could you go
composite.
back to the previous line?
Yeah.
Okay, so how did you calculate delta F using these two equations, solving them simultaneously, or?
Which one?
Delta F.
Delta F, we have this two quantity, del P1, 2, right? And then here we have del F.
Okay.
Yeah.
So yeah, you have del F in both equations, so you solve for it.
Yeah,
using
yeah,
that.
yeah. For the
Okay.
two areas, yeah, area
Yeah,
one
for
and
the
area
tuning.
two. Yeah.
Okay, okay.
But you
So
can see dial-F is common.
yeah, yeah, DALF is common.
It's common.
That's fine.
Dial-F is common, right?
And you
Dial-F is
already know the change in the load. You have the delta PL1, right?
del PL1. Yeah,
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 this is known.
yeah. What is the
Okay.
amount of the load change here?
Yeah, yeah.
Yeah.
And you just solve for delta F.
Hmm. Yeah.
Okay, makes
Okay.
sense. Yeah, yeah.
Then we calculate what should be the amount of power flow through the tie line here, right? So what we observed that this is the generator in the area 1 and generator in the area 2, and we have the load here, right? And again, we can because although there will be frequency sensitive load also, right? Frequency sensitive load in the area 1 and frequency sensitive load in the area 2 as well, right? So thus the turbine output power, it will depend upon what is the droop. And then again over here, it will depend on what is the droop over here. So the now if I say dial P12, it is this direction of the power flow, right? So here, this is one from area 1 to 2, but there could be a power flow direction from 2 to 1, then you will write this way, del P to 1. So what I mean to say, del P12 will be equal to minus of del P21, right? It is just the sign convention indicating the direction of the power flow from 1 to 2 or 2 to 1, basically. Okay. So with this, now if we have, let's say, load increase in the area 1, so it will also lead to frequency change and in fact reduction uh, in the both area because the system is interconnected, and thus you have the power flow to the tie line. Yeah, this is what I refer. Minus del P12 will indicate power flow from area 2 to 1, and that we can say as del P21. We can say this way. So minus of del P12 means power flow from a 2 to 1 here. And the tie line power flow deviation, it will depend upon what is the regulation characteristic. Yeah, so that means what is droop and what is the load damping constant here. Similarly, we can write down what is the frequency deviation uh, defined in the system when you have load change in the area 2. So here it will be, in fact, it should be del PL2 actually here, del PL2. It is the same way. And then what is the composite frequency response characteristic? It is the same form of the relationship what you have it here. It is the same form. And then the power flow through the tie line, it is the same way. And the previous one, what you had it.
So this equation, if I may ask, this will
Yeah.
give you the optimal power flow to reduce the delta F, or
No. One thing again, as I said that optimal power flow, we do it based on economic generation, right? It is based on economic generation. But this change in the schedule power flow, uh, uh, we don't do it as economical way, basically. Because this change in the, because load is dynamic, right? You have dynamically varying load disturbances taking place every minutes and so on. So this supplementary control will be applied on generator, on selected generator, right? This is one part, very clear. But that selected generator can be the economical generator. And that economical generator, you get it after solving the optimal power flow. Okay.
Okay, so the generator you select to apply the secondary control is the most economical one to
Yeah, yes,
for
that
generation.
we do it. That we do it. Yes. Yeah.
Okay. So
So where
if I have renewable sources, for example, let's say I have solar
uh,
or PV or wind in my system. In
uh,
that case, I will prioritize taking the power from them, right? Rather than taking the power from conventional fossil fuel or gas turbines, right?
okay,
Is that the like the
but
idea of this
but one
economic
thing,
generator?
no, but one thing, yeah, uh, economic generation. Okay, we can have from the renewable. That's another part. But one thing to mention here that here we want to schedule power flow, right? And scheduled power flow will be based on those generation resources which are dispatchable. Let's
Ah,
say,
okay.
but if you say that, okay, the load has changed, but you want to increase the output power from your resource. And if you say the resource has PV or the wind, and let's imagine that you don't have wind or the solar, then you cannot schedule the output power from those generation resources. I mean, the renewable resources. It is not possible.
You're right. I see your
So
point.
in
Yeah,
that
yeah.
sense, it
Because usually you just operate at maximum power for solar and wind.
yeah, they
You
are not
extract the
dispatchable
maximum
basically.
power
Yeah,
unless you already are operating and less than maximum for any
Mm,
reason, then you can afford to go higher,
yeah,
right?
then it will be possible because if
Yeah,
you have wind available or solar available, but if you have solar and wind available, then why don't you generate to the maximum? You will always go for
exactly.
the
Yeah,
maximum
yeah. You should
position.
always go for the maximum. Yeah,
Maximum,
makes sense.
maximum. Yeah.
Makes sense. Yeah.
That is one thing, but that's why the LFC problem or the AGC normally we apply it on those generation resources which are dispatchable, either from steam or base turbine or the hydro turbine, basically hydro power plant.
Okay.
Mm. Yeah. So same way, you have these two quantities change in the frequency. If you have the load change in the area 2, and then the power flow. Yeah, we have one example in the book. Uh, you can refer. It is from the Hadith Sadat book. Example 12.4. Here they have it for two area system, and they have given what are the droop, then the load damping constant for the two areas, what are the inertia, then the base power, and then governor time constant and turbine time constants, so on. So using the, here they have said the nominal frequency is 60 hertz. You have some, in fact, the initial operating point and then the power coefficient 2 per unit. You have a load change in the area 1, and then you determine what is the steady state frequency deviation and the Thailand power flow. And also you can make your own Simlink so as to get time domain response of frequency deviation. So this is the load change because this is 187. So on a base of 1000. So this is in per unit here. Then you calculate what is the steady state frequency deviation. And then in hertz, it is this quantity. So what is the new frequency? It will be this. So this is the change in the frequency. You have a load increase, and thus the new frequency will be this one. Then you can calculate what is the change in the turbine power from the 2. areas based on the group that we have. So one area one, you can see 100 megawatt, and area two, you can see it is something 80 megawatt here. And then they have calculated what is the change in the Thailand power, and it is something this one here. So you have this power flow from area 2 to area 1 here, right? And
How do you know the direction of the power flow?
okay, because we had it, in fact, dial P1 2, right? And yeah, because we have the change in the area 1, that is dial omega dial 1. So this was dial omega. This one, this is the steady state value, right? So dial omega, and then per this much change in the megawatt, I mean something 3 megawatt, that because this is what you get in per unit here, 0.03 per unit. So this is because you have a base of 1000, so it is something 3 megawatt change minus. Then same way you do it for area 2 here, and this, the change will be this much megawatt. So the change in the total area load, in fact, it is something 4.5 and 3 here. So it is this much. And then you calculate what is the Thailand power flow here. Because you have the frequency deviation minus here, right? You have the load change,
Okay.
this one, right?
But it says here P12,
Mhm.
and here it says thus it flows from 2 to 1. Is that because it's minus sign, or
Which one? This?
the calculation is P12, right? Delta P12.
Yeah,
This
del
calculation,
P12. Yeah, it is
which
minus
is
sign. Yeah,
minus.
yeah, it is
But
coming
here
from
it does in the next like sentence, it says there is 84.5 megawatts flows from 2 to 1. From it,
Yeah,
not from 1 to 2,
1 to
even though
2.
you calculate
Yeah,
it from 1
because
to
this
2.
is
But here
minus
it
sign.
says,
Yeah, yeah, because this is minus
okay.
sign. Yeah, yeah.
So
Because
when you have a minus sign, that means it flows in the opposite direction.
opposite direction. Yeah, because
Okay.
that's what I said. If you refer, yeah, here itself. Del P12 is positive. It is means the power flow from 1 to 2 here, right? And if in case del P12 is negative, it means that it is from 2 to 1, and it is this one. That means
Okay.
dial P12 negative means it is dial P21 basically.
Okay. Okay. Yeah, that was my question. Yeah, I
Yeah,
just wanted
yeah,
to check.
it is that way. Right. And then if you can make the swim link, and then you can do the simulation in the MATLAB. So you can see what is the frequency profile for the two areas here. And you can say after several seconds, frequency will become, because during the initial stage, you can see the frequency profile for the two areas, they are different here, right? But later stage, the frequency profile for the two areas become same here, right? And but still you find it here, this is the steady state frequency deviation here, right? And here we have shown what is the change in the turbine power for the two areas, and then what is the change in the power flow through the tie line here. This is also shown here. But out of this, some comments are given here. You have the LFC in the primary control loop. You have the change in the power from the area 1, right? And that was met by increase in the generation in both areas. Yeah, so that means load disturbance take place in area 1. Okay, When you have the load disturbance in area 1, in fact, load increase in area 1, you increase the generation in both the areas here, right? This is one part. Second part is that you have the power flow through the tie line, and you also observe frequency deviation, frequency reduction. So these are some of the points you can note here, you observe it here. But in normal operation, it is expected that each area should meet its own load change. All right, so that means if you have change in the change in the load in area 1, then area 1 should meet the demand, and also maintain the tie line power flow at the scheduled value and keep the nominal frequency. So these are normally what we expect. Each area should meet the load demand, maintain the power flow to the tie line, and obtain the nominal frequency. This is what we expect actually.
So why did this not happen?
Uh, okay, we will discuss
Mhm.
this in the
Okay.
next part, right? So do we have a break here? Yeah, for
Okay.
5 minutes. Okay. So as we discussed that with this example, with the load change applied in area 1, the frequency deviation in the two areas, they have different profile, but since the system is interconnected, we get common frequency at a steady state condition. That one. Then we also observe that load change took place in area 1, but we had turbine power change in both areas. Uh, so it means that if load disturbance takes place in area 1, you change the output power, you regulate the output power on the turbine in both the areas. That should not happen because load change is local. Then it is expected that it should be the local generators or the power plants, they should meet the disturbances. The neighboring interconnected system, I mean the power plants or the turbines, which is interconnected to the area 1, that should not be affected. So there should not be any regulation uh, on the output power on the turbine from area 2. This should not exist. Another part, we observed that because initially we had, because this is delta P here, that means change in the tie line power. And what we observed that there is a change in the tie line power here. So that means whatever the schedule amount of power flow which existed before disturbance, pre-event. Now after disturbance, the schedule power flow has changed. So that means again, that means the power flow in the line has changed here. So it is also expected that the schedule power flow should not change here. It should become zero at a steady state. This is what we want. And then same way, the turbine power in the area 2 should not be disturbed. And we want the frequency restored back to uh, zero value here, nominal value. We should get the frequency to the nominal value, which we want here. So for with these desirable characteristic in the system response, there would be some modification here. So we have some objectives towards the generation control. And First one is that we should be able to maintain the system frequency within the limits, have the interchange of the power flow at schedule value. So if there is some disturbance, this should not be disturbed. It should be as per the scheduled value. And the since the system is interconnected, and thus the common frequency change should be within the stipulated time actually. That means it should not be lagging, because as you can see here, what you find here, that the frequency, the common frequency, it is in fact after 15 seconds or 20 seconds something, yeah, but it is expected that frequency should be restored back in a good enough time. And thus, with these objectives in mind, we will formulate a control law, we call it as, and that is sometimes we say it as area control error. So we design a control signal for each area with a control law given as area control error. This control signal, area control error, will have two components here. The first one is the tie line power deviation here. What is the power flow deviation? The first component in the control signal here. And second part is the frequency deviation. But we have uh, frequency deviation with the weight introduced, and that will be as a in terms of a bias factor. So here we introduce a frequency bias factor, which will be basically the regulation characteristic as we have discussed earlier. So 1 by R plus D. So this will be the frequency bias factor for each area here. That will be introduced in the second part for the control law formulation. That is the control area control error signal. And thus now we will be able to have this in the secondary loop automatic generation control uh, to be applied through economical generation. So, and thus from the previous slide, now we write down what is the control signal, which is basically the area control error. And this area supplementary control signal, it is added in the primary control loop through the integral controller. And thus the control signal, it is now, you can see, it is formulated as summation of power. So this is actually the tie line power flow. From it could be from 1 to several number of areas, depending upon how many areas you have. So del P Ig plus the bias factor and then frequency deviation. So this composition of the relationship, what we have it for the control signal design, it is based on this formulation, what we had it. The tie line power flow and the frequency deviation weighted by a bias factor here. So we have now area control error signal written down mathematically. So as I said, BI is the frequency bias factor. And here you can have, as I said, for several areas and areas. So there could be combination of area control error signal here. And which will have several terms with the tie line power flow and the frequency here. And since we have the integral controller in the loop, thus we can reduce the area control error signal to 0 value here. And with that, Now here you can see how we apply the AGC. And you can see that within the interconnected system, right? We have the measured frequency. We have the interconnected system, so we have the measurement of frequency. What is the nominal frequency here? Then we had the frequency error here, the Bass factor. We get this product. And then we have several interconnected systems. So what is the amount of the power flow from several of the lines here, right? We sum it. And then we have also some decision at the centralized control level, what should be the scheduled amount of power flow in the network, this quantity. And then you obtain what is the error in the tie line power flow. So that means the difference of the two. What is the scheduled amount of power flow in each of the tie line, and what is the actual amount of the power flow in the tie line. We have the measurement here. And then this is the net change. And since we have this AGC for each area on the selector generators, so here this is the area control error signal, which is the summation of tie line power flow from each of the lines, tie lines, and then the Bass factor times the frequency deviation. We have this filter to remove the harmonics and the high frequency components. We do that part. And then here we decide where to apply this area control error. That means on the selected generator. And this will be based on which generator is economical in the generation. So we have some algorithm for economic allocation here, that part. And
So
then
the area error is calculated for each area, but you
uh,
don't.
yeah, it is for each area. Yes,
Okay, and then
AGC,
you don't, but you don't apply it for all the areas. You only apply it
not
for
for all,
some area.
not for all, not for all,
Okay,
not for all. It
and
will
then
be
you.
only on selected. That's why we have
Oh,
this one, economic
okay,
allocation. That's why we
okay.
have it, right? And then we have these signals because this part, remember, this part we will do it at a centralized location. This will be at a centralized location, and then the control signal will be transmitted. Let's say you have the interconnected power plants and the system, and then you also have the communication network established between the system. It could be through your optical fiber cable. So you have the power flow, you have the signal flow. That means the control signal flow through this channel equipment. It could be the optical fiber cable here. And then you apply it on through the integral controller. Yeah. And that will change what should be the uh, turbine output here. So you have this say signal applied on several generators or be on the selected generators where you have the AGC basically. So this is the integral controller, but it could be for selected generator because we go for economic allocation. So it will be on selected generator here, right? Maybe I have one more diagram to illustrate a little bit bigger way on this part later on. So with this, the previous equations now are modified, and we write down what is the area control error for area 2 here. And then similarly, we write down for area 1 here. So you can see area control error is defined for each area, in fact, which is the sum of the tie line power and the frequency Bass factor here, product of the two. And next one, here again, point is that how to select the frequency Bass factor. That should be what should be the criteria here. And We have the integral control action, which will ensure the area control error signal to 0. And but we do have this analysis for two area system, and thus we write down area control error for each of the areas equated to 0 here. Now, with this being considered equated to 0, we can have this quantity 0 or dial up to be 0 for all other non-zero values here. So A1, A2, B1 or B2, what you have it here. So for these non-zero values, so we can have these two quantity, these two parameters as 0. And to get that, in fact, we just understand that whenever you have the increase in the load, it will result to frequency decrease, and then you will have the governor action, and it will be through the primary loop here in both the areas. And then it is the primary control loop which will try to avoid the maximum deviation, and thus the primary control loop will be in action for the few seconds, and it will try to restore the frequency back to the nominal range. But again, this could be further improved. This frequency regulation could be further improved with the secondary control loop. And thus here this quantity, we define it as regulation characteristic. And so now I think if you refer back to the previous slide.
This delta FR is like the steady state frequency deviation.
Yes, regulation characteristic, regulation
Okay.
frequency, because we had this delta F here also, but here we
Yes,
have
yes,
not
yes.
defined it basically, right? But
Okay.
now when we have the area control error, in this case, we define this regulation, delta F regulation here for both the systems. And then, so the previous release figure, what we had, and now it is slightly modified here. So you can see that you had the droop, you had the governor, you have the turbine, and then you have several turbine generators set here, right? So you have another turbine and then the governor in the area 1 here. And this is the droop 1 for this turbine. And again, because since you can consider several several generators in the power plant, so let's say the same droop, but it can be a different droop as well, no problem. And here you can see that area control error is applied on one of the generating set here. This area control error, you don't have it on this turbine generating set, right? So the modification, you have it only on on the selected generating set here. So you have the Bass factor, because this is delta omega, dial omega here, Bass factor, and then del P12, which you have it extended from here, and this is your area control error signal. And then you have the integral and you feed it here. So this is the supplementary control signal here, this part, which you have it here. It is the supplementary control signal. And this part of the loop you have, this one, this is the primary control loop here. This is the primary control loop for the turbine 1, and this is the same primary control loop for turbine 2. But inclusion of this one with through area control error on this turbine, this will form the supplementary control loop. And same way you have it for area 2. So you can see turbine 1 also, and then the turbine 2 you can say, and area control error in area 2, it is now on turbine this turbine, and it is in the same way. So here you have the AGC on selected units, selecting generating units here. So you don't apply AGC on all the generators in the power plant or several power plants, but on the selected generators or on the selected power plant here, it can be. So this is the modification, and that this forms the supplementary control loop for the load frequency control or for AGC, automatic generation control here, because this quantity here, that will be the scheduled amount of power flow. It will be, and that scheduled amount of power flow will be based on this signal here, right? Agreed?
Yeah.
Okay.
So I have a question. This B1 and B2 constant, how are they determined?
Okay. Yeah, that's what I have the next slide here. Yeah.
Okay.
Yeah. So there could be a deviation in the tile line power flow from the scheduled value, because we said that the deviation in the tile line power flow should be 0. And the supplementary control signal, because this is in the secondary loop, so it will be slower than the primary loop, yeah, primary speed control. And we want to have this. So we will examine the performance of the supplementary control loop with the settings, yeah, with the different settings. So, and for that, let's say the first part, when your frequency bias factor B1 is equal to beta 1 and B2 is equal to beta 2 here. So area control error, we write down in this way. And then with the manipulation, we had this. And then what you find it here, area control error is equal to what is the load change in the area 1. And however, for the area control error for area 2, with this relationship, and what you find it here, it will be 0 here.
Why is it 0? Is it because we chose area 1 or?
Yeah,
Did we
you
set
have
this to 0 or did we
yeah, this is
calculate
the
it?
general relationship.
Okay.
Yeah, and then minus, we get it minus beta 2 and plus beta 2 here.
So this is 0.
So it is 0 here. However, for area 1, area control error, that comes out to be what is the load change in the area 1 here.
Okay.
So if you have B1 and B2, that is beta 1 and beta 2, then that means the setting of equal to the composite frequency response characteristic, right? Because beta 1 and beta 2 are the composite frequency response characteristic here, right?
Okay.
So if the bias factor, frequency bias for B1 and B2, they are the frequency bias factor, and they are here beta 1 and beta 2, they are the composite frequency response characteristic here. That is 1 by R1 plus D1 here, right? So if the bias factor is equal to the composite frequency response characteristic, then we get these two, right? So here you find that the supplementary control in area 1 will respond. So that means load change takes place in area 1. So the supplementary control in area 1 will be in action. There will be no change. In fact, there will be no response. There will be no response of the supplementary control loop in area 2 because it is 0 here. So that means the load change in area 1, it is unobservable to supplementary control loop in the area 2. And this is very much obvious because load change has taken place locally. So it is very much expected that the control error, The control error in area 1 should respond against this load disturbance. The control error in area 2 should not respond. So, and that's why it is 0 here. So this is what we want here, right? This is the case when you have this setting. But if in case you have twice of it, if the frequency bias factor, there are twice of the frequency composite frequency response characteristic, then with this relationship, we have the substitution, and then what you find it here, this quantity, and then same way for area 2, you have it this one here. In this case, you find both area 1 and area 2. The supplementary control in area 1 and area 2, they will be in action against the load change, a load change in area 1 here, right? And their correction, towards the frequency profile, twice as fast. This will be almost double. So that means the correction in the frequency profile will be much faster here. But one more point to observe, that there will be a generation in area 2, and it will be out because here you have area control error in area 2, so it will based on this quantity. So thus there is some response because of the supplementary control loop in area 2. This will take place. So when you have these two settings here for the two, but again you can have several combinations, basically 1.5 or 0.5 and so on, and then based on, you can see what will be the area control error 1 or area 2 and so on. So you can have several combinations of this actually.
So how do you determine which one is the best one?
The best one, if I say this one, because if we find that it is the supplementary control area 1 that will respond against this change, but in area 2 it does not respond. So this is what we want here. So this
So
setting,
is it always like this? This setting is the
in most
for
of the
all
cases,
contingency levels? Or?
in most of the cases we have this setting.
Okay.
So thus with the same example that we had the previous one, and we have the load change applied in area 1, and now we can see the time domain response here. The frequency profile during the initial stage, it was something different because it will depend upon what is the inertia and then what is the load damping constant factor here. But later stage, what you find that you have a common frequency, and again the frequency deviation becomes 0 here. This is first part. And second part, you observe that since the load change took place in area 1, and thus you have the turbine power, some transient response, but it settles down to a steady state value. So this is the amount of change in the turbine power in area 1. However, if you refer it for area 2, though there is some transient response here, but it settles down, to 0 value. And same way, similarly, the Thailand power deviation, that also settles down to 0 value. And these results, what we have it when bias factor is equal to composite frequency response characteristic for the two areas. It is with this one. So this is what we achieve when we have the selection of the frequency bias factor equal to composite frequency response characteristic as this quantity, right? Anything on this?
Yeah, it makes sense now.
Okay, Andreas, anything?
No.
Then we have, in fact, simulated result for the system for the same example. And here you can see when the frequency Bass factor and the composite frequency response characteristic is this one. So we have this profile, and this is the case when you have twice of it actually. And in this case, you observe this is the turbine power, and you find that the turbine power in area 2 has few oscillations, but it settles down to final value. Yeah, and then again, Thailand power deviation is also near about 0, you can say. But with this twice of the frequency response characteristic, loosen characteristic as Bass factor, you find that there are more swing in the frequency profile here, frequency deviation profile here, and it does not settle down quickly. Yeah, but in this case, it settles down quickly here. This is what we achieve with this one, with this setting for the frequency Bass factor. So maybe I stop here then, right?
Okay.